Assalamualaikum, my dear students. Welcome back to Chapter 7 Haloalkane. Today we are going to learn Lesson 70, Nucleophilic Substitution of Haloalkane. There are three types of nucleophilic substitution reaction on haloalkanes. Number one is with H2O and sodium hydroxide. Number two is with ammonia, and number three is with potassium cyanide. We need to be able to explain their mechanism. So we have to learn Sn1 and Sn2 and then compare the hydrolysis activity of primary, secondary, and tertiary haloalkanes. Next, we need to show the stereochemistry in the Sn2 mechanism using three-dimensional formula and indicate the rate determining rate and order of reaction in Sn1 where necessary. As we have revised earlier, haloalkanes are polar compounds because having halogen atom, which is more electronegative, making the carbon attached to it is electropositive and react as electrophilic site. Being an electrophilic site, it is prone to be attacked by a nucleophile. Nucleophile will attack the positive center of the electrophilic site, as shown in this diagram. In this lesson 70, we are going to focus on nucleophilic substitution only. This reaction has two types of mechanism, Sn1 and Sn2. So let's focus and try to understand it clearly. Let's look at page 263, our mind map page. As I've mentioned earlier, there are three reactions for nucleophilic substitution. The first one that I've mentioned before in the objective of the lesson is the reaction of haloalkane with sodium hydroxide aqueous in the environment where we have a lot of water. So it's going to use a reflux condition as well. This reaction is going to produce an alcohol as the product. The second nucleophilic substitution is the reaction of haloalkane with ammonia in the presence of ethanol and reflux. The product is going to be an amine, whereby if you have an excess ammonia as reagent, we're going to produce a primary amine, and this primary amine is going to react with the product and is going to produce a secondary amine. Secondary amine, in a condition where we don't have excess ammonia, is going to react back with the product and is going to form tertiary amine. So this is basically how we produce the three categories of amine in chapter 11. Right. The third nucleophilic substitution would be the reaction of haloalkane with potassium cyanide in the presence of ethanol and reflux. We are going to produce RCN, a cyano compound, and this cyano compound is not stable and it is going to form further an amine, a primary amine, with the reaction of reduction agent LiAlH4, ether, H3O plus, and H2 with PT or PD or Ni heat. These are the reduction reagents. And we can also treat it with sulfuric acid in heat and water environment, where we're going to produce carboxylic acid. As you can see here, we have already entered a bit of chapter 8, hydroxy compound, a bit of chapter 10, carboxylic acid, and mostly chapter 11, amine. Please fill in that page now. For example 7.5, let's listen to Madam Tipa explaining how to answer these questions.
The haloalkane can react with KCN in alcohol and reflux to form cyano compound. Okay, so how to draw the cyano compound? Okay, this is nucleophilic substitution. And nucleophilic substitution. Okay, so in the substitution, okay, in substitution, okay, the Br will be replaced by Cn. Okay, the Br, okay, the bond will break here. Okay, this Br will be replaced with Cn. Okay, so the product after the reaction with KCN will be CH3, CH2, Cn. Okay, I'll draw it here. CH3, CH2, Cn. Just have to replace the Br with Cn. That's all. Okay, after that, okay, the cyano compound can react with lithium aluminium tetrahydride in ether and H3O+. Okay, lithium aluminium tetrahydride LiAlH4. Okay, so this reaction is actually called reduction. Okay, so under the reduction, very easy. Okay, just have to focus on the Cn. Okay, focus on Cn. So in the product, okay, the alkyl group will be the same. Okay, we still have CH3, CH2. Okay, the Cn, okay, the purple one that I highlighted with purple color, will change to CH2 and H2. Okay, so this is the purple part of our product. Okay, and this is actually a primary amine. Okay, primary, not 10, primary. Okay, primary amine. Okay, where we can name it as 1-propanamine. Alright, so this is reduction. So when I said reduction, means we are adding the hydrogen. Okay, oxidation, we add the oxygen. Okay, so the next reaction, the cyano compound can undergo hydrolysis. Okay, hydrolysis is a reaction with water. Okay, the easiest way to remember, react with water. Okay, so the Cn will directly change to COOH. Okay, it means it will produce carboxylic acid, which is called propanoic acid. Okay, but the difference, okay, in the product here, okay, when it undergoes hydrolysis, okay, for the reaction of reduction and hydrolysis, okay, let me write the word hydrolysis first. This is hydrolysis. Okay, the number of carbons, okay, has been increased. Okay, from the starting material, we just have 1, 2 carbons. Okay, but now in the final product of the reduction, we have 1, 2, 3 carbons. Okay, so this one also 1, 2, 3. So number of carbon is increased by 1. Okay, this is very important, okay, especially if the question asks you to synthesize. Okay, synthesize the from bromoethane synthesize propanoic acid. So you can use this reaction. Okay, from bromoethane synthesize the primary amine. Okay, so this reaction can be used. But if you don't want to increase the number of carbon in the product, final product, in the synthesis question, okay, you have to choose other method. So this method is not suitable. Okay, because number of carbon will increase by 1.
For example 7.5 just now, these are all the reaction equations that have been discussed separately. Right, the second reagent for nucleophilic substitution reaction on haloalkane is aqueous solution of sodium hydroxide or potassium hydroxide. Here, we are going to use an aqueous form, meaning that the base is having a lot of water so that it is a diluted solution. Together with reflux, is going to substitute Br with a hydroxy group. So let's do the product here. CH3, C, CH3, CH3, and the Br is going to be replaced by hydroxy group. May I remind you that this is a really similar reagent having a reaction on haloalkane, because previously in chapter 5, when we are synthesizing alkene, we have actually learned about a mechanism called elimination, where we're going to use the same reagent KOH and reflux, but we are not going to use a diluted solution. We are going to use a solution ethanol instead. Ethanol is also used short form ETOH. So we are going to have, what are we going to produce? An alkene. So here we are going to get a different product. This one is an alcohol and this one is an alkene. The reactant is the same, haloalkane here, but the only difference is the existence, the presence of ethanol in the condition of the reagent. I hope you should be able to distinguish and differentiate this reaction clearly. Now, the third reagent that we're going to do nucleophilic substitution reaction on haloalkane is ammonia. They are actually three stages, where the first part is we're going to use excess NH3 ammonia, and then the product from this is going to be used further in the next stage, the second stage, to produce secondary amine, and then that product is again going to be used in the third stage when we have limited ammonia.
Okay, let's see example 7.7. Okay, 7.7 we have chloroethane as the starting material reacts with excess NH3. Okay, so for the structure of NH3, okay, actually we have trigonal pyramidal. Okay, so we can draw it like this. I'm not going to draw it in 3D because I just want to show how we get the product. Okay, so what happened here, in the haloalkane, the bond will break between CH2 and Cl. Okay, so the Cl will be replaced by, okay, the Cl will be replaced by the NH2. Okay, but how we get NH2? Okay, we actually will have to break one of the bond between N and H, and this H will combine with the Cl to produce the byproduct, which is HCl. Okay, so the product that we will get, the main product is actually CH3, okay, CH2 bonded with NH2. Okay, so that's the product of this reaction, which is called ethanamine. Okay, and then let's go to number 2. Okay, number 2 we have Cl. Okay, I'll draw it in blue. So the blue Cl there. So what happened in this reaction? The bond will break okay, will break between CH2 and Cl. Okay, and then in the amine, okay, the bond will break between the N with one of the H. Okay, let's say this one. Okay, so that will form the byproduct, which is HCl. So the main product, okay, the main product, you just have to combine, okay, CH3, CH2 with N, okay, with NH, which already attached with the alkyl group CH3, CH2, CH3. Okay, so this is the reaction which will produce a secondary amine. Okay, so first example just now we have ethanamine. This one we can classify it as a primary amine. Okay, so how to classify amine we will learn further in chapter 11. Okay, but in the meantime, okay, you just have to know to classify amine. It depends on the number of carbon that attached to N. Okay, so different with other classification, okay, other functional group classification. For amine, special for amine, the classification depends on the number of carbon or number of alkyl group attached to N. Okay, so if only one carbon or only one alkyl group attached to N, we name it as primary amine. Okay, we class it as primary amine. Okay, so in the second example, we have two alkyl groups attached to N. Therefore, we can classify it as secondary amine. So this is actually the preparation of amine. Okay, now let's go to reaction number 3. So under reaction number 3, okay, the bond will still break between the CH2 and Cl. Okay, we still have chloroethane there. Now we see in the amine structure, okay, if we expand it a little bit, we actually have a secondary amine. Okay, secondary amine, which is CH3, CH2 bonded to N, okay, and then the N is bonded to CH2, CH3. And N has one more H. Okay, so the bond will break between N with one of the H, okay, to produce, okay, if you refer to here, we can draw the product. Okay, this reaction still needs the ethanol and reflux. Okay, so the product that will be produced, okay, the byproduct that will be produced is the HCl. Okay, still HCl. Okay, so this H will combine with the Cl. Okay, so the product now is the CH3, CH2 attached to N, which is already attached with CH2, CH3 and another CH2, CH3. Okay, so now, okay, the tertiary amine is produced. Okay, tertiary amine. Okay, why tertiary amine? Because we have 3 alkyl groups or 3 carbons attached to N. And actually, we can have maximum 4 alkyl groups attached to N. So, we can also have quaternary ammonium salt. But I'm not going to discuss it now. Okay, we will discuss it further in chapter 11 later. Okay, so in the reaction of haloalkane with ammonia, we can have reaction with ammonia, excess ammonia. The product will stop at primary amine. Okay, the product will stop at primary amine. So if you want to produce primary amine only, that do not have any further reaction, we have to use excess ammonia. Okay, but if you don't want to produce a primary amine, let's say you want to produce the secondary amine, the tertiary amine and so on, okay, you can react the haloalkane with the not excess ammonia. Okay, how to differentiate if you are given equation in the question? okay, it is not written as excess. Okay, it just written NH3, so that one will be producing other than primary amine. Okay, so we can also have reaction of haloalkane with ammonia, with amine. Okay, for example, in example number 2 here, we have reaction of haloalkane with primary amine, okay, to produce secondary amine. Okay, we can also have reaction of haloalkane with secondary amine, okay, to produce tertiary amine. Okay, so the mind map is not direct reaction. You need to understand how to use it. So based on this example, this is how we use the mind map to answer the question, okay, to get the product.
Listed here are all the equations that we have done in the video with Madam Latifa separately. For example, 7.7. A very unique and distinguished thing that we are noticing for nucleophilic substitution on haloalkanes are that they have two different mechanisms for one reaction. The reaction is nucleophilic substitution, but we have two types of mechanism, Sn1 and Sn2. Substitution, nucleophilic, one is uni, or one product in the first step. And bimolecular, Sn2, S is substitution, nucleophilic, and 2 stands for the bi, or two products or two compounds during the first step of the mechanism.
Okay, Sn1 mechanism or nucleophilic substitution mechanism Sn1 involve two steps. Okay, in the first step of the mechanism, okay, we have the formation of a carbocation, which is also classified as rate determining step. Okay, in this step, we have haloalkane. Okay, actually here we have tertiary haloalkane. Okay, where the carbon is actually delta positive, okay, more electropositive, and X is more delta negative or more electronegative. So all the bonding electrons, okay, the bonding electrons is actually the bond between the X and C. Okay, this is the bonding electron. Okay, all of the bonding electron, we have two electrons in the bond between C and X. All will be attracted to X. Okay, so this will make the bond between C and X break. Okay, so this will break the bond between C and X, leaving, okay, the carbocation and the anion. Okay, forming the carbocation and anion. And this reaction has slow rate of reaction. Okay, because when you want to break any bond, you have to do it slowly. Okay, so this is also called rate determining step. Okay, in the next step, we call it nucleophilic attack on the carbocation. Okay, so just now we already formed the carbocation, which is tertiary carbocation. Okay, so the tertiary carbocation will react with the nucleophile, or actually the nucleophile, which is rich of electrons, will be attacked by the carbocation. Attacked by. So that's why the arrow is from nucleophile to carbocation. Okay, nucleophile is attacked by the carbocation. So this is a fast reaction. Okay, the rate of reaction is fast because we want to form a new bond. So the product form will have nucleophile attached to the carbon. Okay, so this is a nucleophilic attack. Sorry, nucleophilic substitution Sn1.
Now, if you notice in the mechanism of Sn1 just now, we use the reactant tertiary haloalkane. Why? Because tertiary haloalkane has tertiary carbocation. Tertiary carbocation is more stable. The rate of reaction will be governed by the stability of the carbocation form. So the most stable would be tertiary, followed by secondary, followed by primary, and the last one is methyl halide. Meaning that, as you can see in this scale here, the more reactive haloalkane would be the one that has the tertiary carbocation here, followed by secondary, followed by primary, and lastly, the methyl would be less reactive towards Sn1 reaction. So, as we go through the chapter 7, when we find a tertiary haloalkane, we would immediately thought of doing Sn1 mechanism onto it because it has tertiary carbocation which is more stable, making the product more stable. Basically what I'm saying is, if we want to decide whether we want to do Sn1 or Sn2 on the haloalkane, we need to determine the classification of the haloalkane first. If the haloalkane is tertiary haloalkane, then we will do Sn1 onto it because of the stability of carbocation. Another special attribute that we're going to learn on nucleophilic substitution mechanism is its Sn1 would have rearrangement reaction, whereby when necessary, we are going to shift either hydrogen atom or methyl group. They are called hydrate shift and methyl shift. Why do we need to do this? Because we need to form the more stable carbocation. So, for hydrate shift, we are going to move the hydrogen atom from the carbon atom number 1 to the carbon atom number 2. So, we call the adjacent 1-2 carbon bonds as hydrate shift 1-2 rearrangement of hydrogen atom. For methyl shift, it's the same thing, whereby we're going to move one methyl group from carbon number 1 to carbon number 2. So it moved to the side of the original place. So we call this rearrangement as 1-2 methyl shift. Let's look at the next examples. There are 3 of them. So one for each shift. Please look at it closely. The first question in example 7.8 is, show the mechanism for the following reaction. As you can see here, the haloalkane used is a tertiary haloalkane. So we're going to do the same mechanism as being taught in the previous general mechanism example.
Okay, so we have the reaction of 2-chloro-2-methylpropane with KOH aqueous and reflux to produce 2-methyl-2-propanol. Okay, so as what we have discussed just now, okay, we have 2 steps of the mechanism. Okay, so the first step of the mechanism, okay, we have to do the reaction which is the formation of the carbocation. So how we want to form the carbocation? Okay, step 1. Okay, I will write the name of the step like that. So we have the starting material, okay, where the C carbon is delta positive, Cl is delta negative. Okay, so in this reaction, the bond between C and Cl will break heterolytically. Okay, because the Cl is more electronegative, it will attract all the bonding electrons, the purple bond here, to itself, towards itself. Okay, so it will leave the carbon as carbocation. Okay, which is actually the tertiary carbocation. Okay, I circle the charge just to give some stress there. Okay, just to stress that is the carbocation plus with the Cl minus the anion. Okay, that's why I said just now this is heterolytic cleavage. And the arrow of mechanism that we use is double-headed curve arrow. Okay, and in this reaction, we want to break the bond, okay, between C and Cl. So when you want to break the bond, we have to do it slowly. So the rate of reaction here is slow. Okay, so that's the first step. Okay, now let's go to the second step. Okay, for the second step, for step 2, okay, it involves the nucleophilic attack on the carbocation. Nucleophilic attack on the carbocation. Okay, so we rewrite the structure of the carbocation that we got in step 1. And this carbocation will react with the nucleophile. And the nucleophile here, okay, we have the reaction. Okay, go back to the question. Okay, we have the reaction with KOH. Okay, so the nucleophile used in this reaction is actually the OH minus. Okay, so I will use OH minus only. Okay, so in the second step, okay, the carbocation react with the OH minus, which is the nucleophile. And nucleophile. Okay, so what happened here? Okay, to make sure that you remember to make it easy for you to remember the arrow of mechanism, remember this. The nucleophile, which is rich of electron, will be attacked by the carbocation. We use passive words here. Okay, the nucleophile will be attacked by the carbocation. Okay, so the product will be formed, okay, where the nucleophile, which is the OH minus just now, will be attached to the carbocation. Okay, so that's what happened in this reaction. Okay, so we have the new product, okay, which is nucleophile, which is the OH minus attached to the C plus. Okay, so there you go. We get the product 2-methyl 2-propanol. Okay, I'm going to tell you a story to make it easy for you to remember this mechanism. Okay, so let's say C and Cl. Okay, go to step 1. C and Cl is not a happy family. Okay, let's say C and Cl is not a happy family. Okay, so one day they decided to break up. Okay, so C break with Cl. Okay, C break with Cl. Therefore, we will get the dude and gender. Okay, so the most important here is the dude. Okay, so this is the step where the bond is broken. Okay, so if you are in any relationship and you want to break that relationship, please do it slowly so that so that your partner will not be shocked Okay, so do it slowly when you want to break up. Okay, and then second step, okay, you go to second step, nucleophilic attack. Si Duda, okay, meet somebody and he like her. Okay, so when you want to make any bond, okay, you have to do it fast. Okay, I forgot to put the rate of reaction there. Okay, when you want to make a new bond, when you want to make a new relationship, make it fast. Okay, so that nobody will take her or him before you. Okay, so in this step, okay, the C plus will attack the OH minus, or in other words, the OH minus, okay, or the new the new person here will be attacked by the C plus. Okay, so they will form new family. So this is how we want to remember the mechanism. But please don't write that story in your answer if the question come out in your individual assignment or final exam later.
The second question for this example is involving a compound of when you have a bromine attached to a primary carbon. So this is basically a primary haloalkane. The reactant for this reaction is 1-bromo 2,2-dimethyl propane. So let's look at how the product is having the hydroxy group attached to the most stable carbocation, which is the tertiary carbocation, by doing 1,2-methyl shift rearrangement. Let's proceed. Madam Tipa.
Alright, let's go to example 7.8, question B. Okay, in page 256. Okay, so the step are the same with the first example just now. Okay, let's show the mechanism. Okay, so we have in step 1 formation of the C plus. Okay, so in step 1 we have the starting material, okay, which is 1-bromo 2,2-dimethyl 1-bromo 2,2-dimethyl. Okay, I'll draw like this, dimethyl propane. Okay, and then what happened in the first step? Okay, what happened in the first step? C is delta positive. Okay, carbon is delta positive, while Br is delta negative. Okay, so the bond will break heterolytically, okay, between C and Br. And all the bonding electrons, the purple bond here, will go to Br because Br is more electronegative. Okay, so Br will attract all the bonding electrons towards itself. Okay, and this is a rate determining step, okay, where the reaction rate is slow, okay, because we want to break the bond. Okay, so we will get the carbocation, okay, which is actually the primary carbocation. Okay, primary C plus, and the anion, which is the Br minus. Okay, so that's the first step. Okay, if you refer to first example just now, example A, okay, you can see second step is the nucleophilic attack. But for this question, we cannot go to the step 2, the same step 2. Instead, we will do rearrangement first. Okay, how we want to know that we have to do rearrangement? Okay, look at the carbocation structure. Okay, you have primary carbocation, okay, and the adjacent carbon, or the neighbor, the neighbor of the carbocation. Okay, we have, okay, the neighbor or the adjacent carbon is actually this carbon, okay, which I color as green here. as the cause here. Okay, so this is the adjacent carbon. So the adjacent carbon of carbocation has two methyl groups. Okay, so we can rearrange the methyl group, okay, to form a more stable carbocation, which is actually the tertiary carbocation. Okay, how to do it? Okay, let's go to step 2. Okay, so step 2 in this reaction is rearrangement, and we will do now the 1,2-methyl shift rearrangement. Okay, so we redraw the structure of the carbocation that we got in step 1. Okay, which is the primary carbocation. Okay, I will draw the plus at different position now. I will draw it here. Okay, because I want to show the formation of the rearrangement just now after this. Okay, so what will happen here? We will change the position. Okay, we will change the position of the carbocation. Okay, with the methyl group. Okay, we will change the position of the carbocation with the methyl group. Okay. So 1,2-methyl shift. Okay, this is carbon number 1, this is carbon number 2. So we change the position. Okay, so just draw the arrow like that. Okay, the arrow must be double-headed curve arrow. Okay, just draw this arrow. Okay, so we will get, make sure you write it here, 1,2-methyl shift. Okay, to tell the what is the what type of rearrangement that you did. Okay, so CH3C. Now the carbocation will change to carbon number 2. Okay, so carbon number 1 will get the CH3. Okay, so it becomes like that, like this. Okay, and now we have the tertiary carbocation, which is more stable than the primary in the previous step. Okay, so this tertiary carbocation will be used to form the major product. Okay, very sorry. I'm very sorry because the arrow of mechanism here should be from methyl. Okay, methyl change place with the C+. Okay, like that. Okay, so we have formed the tertiary carbocation, which is more stable in this reaction. Therefore, the next step we will follow the second step in the previous example. Okay, which is the nucleophilic attack. Okay, step 3, nucleophilic attack on the carbocation. So we redraw the structure of the carbocation that we have formed in step 2. Okay, which is the tertiary carbocation, which is the most stable carbocation here. Okay, and then it will react with the nucleophile. Okay, what is the nucleophile? Okay, go back to the question. We have reaction with KOH. Okay, so reaction with KOH means we have nucleophile OH minus. Okay, so the nucleophile is OH minus. So back to step 3. Okay, so this carbocation will react with the OH minus. Okay, what happened here? The OH minus will be attacked by the carbocation. Okay, so the OH minus is attacked by the carbocation, and the reaction is fast. Okay, and the product or the major product will be formed. Okay, where the OH is actually attached to carbon number 2 instead of carbon number 1. Okay, so that will be the major product of this reaction. Okay, so the major product of this reaction is, okay, if you give the numbering to the carbons, okay, we will see that we have 1, 2, 3, 4 carbons. So the major product is 2-methyl 2-butanol. Okay, so I'm going to write it as major here. Okay, so this is why the major product is not the OH substituting the Br at carbon number 1. So that one will be the minor product. So major product is formed when we do the rearrangement 1,2 methyl shift for this reaction.
The third question for this example is also a primary haloalkane where you can see the bromine atom is attached to a primary carbon. As you can see, the hydroxy compound is basically attached to a secondary carbon as the tertiary carbon is quite far away. The thing that is happening here is 1,2 hydrate shift. This would be the major product of this reaction. Let's listen to what Madam Latifah has to say.
Alright, let's see example 7.8, page 256, question number C. Okay, question number 3C. Okay, question C. So, in this reaction, okay, we have a primary haloalkane as the starting material. Okay, primary haloalkane. So we can predict that the carbocation form will be the primary carbocation. Okay, but this question have given you the hint involved 1,2 hydrate shift rearrangement. Okay, so in step 2 we will do the rearrangement 1,2 hydrate shift. Okay, so let's look at the first step of the mechanism. Yeah, first one is the formation of the carbocation. So C is delta positive, Br is delta negative. Okay, what will happen in this reaction? The bond between C and Br will break heterolytically. Okay, and bond breaking involves slow rate of reaction. Okay, so we will form the carbocation, which is actually a primary carbocation. Okay, so if you see the structure that I draw now, okay, I expand a little bit of the structure of the carbocation. Okay, so right here, so I expand a little bit of these two carbons. Okay, these two carbons, because I want to show after this that two carbons will be used in the rearrangement process. Okay, so now let's go to step 2. Okay, before that, this is actually the primary carbocation form from the first step of this reaction. Okay, now we go to step 2. Okay, so step 2 here involve rearrangement. Okay, how we want to know that we have to do the rearrangement? Okay, 1,2 hydrate shift. Okay, so we refer to the carbocation. Okay, we refer to the carbocation, and then we can see here this carbocation is primary carbocation, which has adjacent carbon that has 2H. Okay, adjacent carbon sebelah. Okay, so the adjacent carbon of the carbocation has 2H, which can be used to make 1,2 hydrate shift rearrangement to form more stable carbocation. Okay, so in step 2 we redraw the structure of the primary carbocation that we got in step 1. Okay, so I will put the plus symbol above, okay, to show the rearrangement. Okay, so the hydrogen will change place with the C+. Okay, so this is a primary carbocation. So after the rearrangement 1,2 hydrate shift, okay, we will get the most stable carbocation, which is a secondary carbocation. Okay, now secondary carbocation is formed, which is more stable than a primary carbocation. Okay, so that's why we have to do this rearrangement to form the major product. Now let's go to step 3. Okay, so step 3 of this mechanism is the nucleophilic attack. Okay, nucleophilic attack. Okay, on C+. Okay, so we redraw the structure of the secondary carbocation that we got in step 2. Okay, secondary carbocation. Okay, maybe you wonder why we do not do 1,2 methyl shift instead of 1,2 hydride shift. Okay, because we can just do rearrangement on from with the adjacent carbon. Adjacent carbon is the carbon next to the carbocation. Okay, exactly next to the carbocation. So although we have CH3 okay in the structure, that CH3 cannot be used in the rearrangement. Okay, so for step 3, okay, we need to react the carbocation with the nucleophile. Okay, go back to the question. So we have nucleophile reaction with KOH. So nucleophile is OH minus. Okay, so we use that OH minus on step 3. Okay, react with OH minus. So the arrow, remember, it must be from rich electron species to poor electron species, or OH minus is attacked by the carbocation. Okay, and this reaction needs fast rate of reaction, and the major product is formed. And the major product here is actually OH attached to carbon number 2 instead of carbon number 1. Okay, so we have the major product, okay, which is 3-methyl-2-butanol, okay, as the major product of this reaction.
The second mechanism of nucleophilic substitution is Sn2. This mechanism only involves one step. It is referring to two molecules that involve in this one step. So that's why it is called bimolecular. The two molecules are this haloalkane and also the nucleophile. The nucleophile will attack from the back side of the electrophilic side of carbon, and then it will turn into a transition state which has 5 bonds attached to the carbon. This is extraordinary, so it is not stable. The first part here is a slow reaction, and then the transition state will move fast to the product, whereby acts as halogen, more electronegative, meaning that it is a good leaving group. It can take both of the electron in this bond to itself, and finally, nucleophile will be attached to carbon at the back side of the originally haloalkane, or now it has become a new product. So in Sn2 reaction, the nucleophile will attack from the back side of the electrophilic carbon, and this is actually the opposite side from the bonded halogen. Backside attack means that the nucleophile is going to attack the electrophilic site at the opposite side from which the halogen is attached to the carbon. So this will cause the product formed has an inverse configuration from the original configuration. It is said that when the tetrahedron of the carbon atom becomes inside out, it looks like the umbrella caught by the wind. Let's look at this video. Yes, the nucleophile is coming from the back, and as it is attached to the center electrophilic site carbon, it is going to make the X leaving the group, and it is going to become an inverse position like the umbrella caught by the wind. Here is the umbrella. So as you can see here, the inversion occurs at the carbon atom, and attacked by the backside, it's going to become like this, the flipped umbrella. Now let's look at the relative reactivities of bimolecular nucleophilic substitution Sn2. We want to know which haloalkane will be reactive when doing Sn2. So the reaction will be faster when the groups that is attached to the carbon or the electrophilic site is smaller. The reaction is faster when the groups are small, and it is slow when larger groups are attached. So here on the right side, as you can see, the presence of bulky alkyl groups will prevent the nucleophilic attack from the back. As you can see, the side chain is actually preventing any nucleophile attack from behind of the bromine or the carbon, which is the nucleophilic site. Let's do one example. 7.9. Show the mechanism for the reaction below. So since this is a primary haloalkane, we should be able to do Sn2 immediately.
Now let's see how to answer the example 7.9 in page 258. Okay, so show the mechanism for the reaction below. Okay, how to know what type of mechanism occur? You have to know the classification of the haloalkane. So this is a methyl halide. Okay, so methyl halide is more reactive towards Sn2 mechanism. Sn2 mechanism. Okay, nucleophilic substitution, bimolecular. Okay, bimolecular nucleophilic substitution. Okay, so bimolecular nucleophilic substitution or Sn2 involve only one step of mechanism. Okay, so we will start with identify the type of nucleophile involved in this reaction. So you can see it here. Okay, you have the KOH aqueous reflux. Okay, so we can determine that the nucleophile for this reaction is actually the OH minus. Okay, so the OH minus will be used in this reaction. So we have OH minus, and then you have to draw the structure of the haloalkane or methyl bromide here in the shape of 3D. Okay, it is compulsory to show the shape with 3D structure. Okay, so this is the structure of the alkyl halide. Okay, 3D structure. So we have CH3 Br. Okay, so backside attack will occur. Okay, backside attack occur where the OH minus is attacked by the C. Okay, so OH minus is attacked by the carbon. Okay, the bond between C and Br will break temporarily. Okay, so bond breaking involve slow rate of reaction. Okay, and the product form. Okay, and what will be formed? Okay, it will form a temporary bond. Okay, with the carbon. The carbon will form temporary bond with the OH and also with the Br. Okay, because carbon have to choose now. Okay, which one that it wants. Okay, whether it wants the Br or the OH. So it forms temporary bond. Okay, and it becomes like this. And when you draw the transition state, okay, make sure you put the negative charge. Okay, because C now has more than 4 bonds. Okay, and label it transition state. Okay, and this transition state is temporary because we will get a new product. Okay, when the Br leave the transition state. Okay, so as I said just now, C have to choose whether it wants to be bonded with OH or Br. Okay, it cannot be bonded to both of them. Okay, therefore, okay, let's say C choose to bond with the OH. Okay, and the H is not involved here. Okay, the H is not involved here because it is not the main character in this story. Okay, so when the bond is broken, okay, between C and Br, okay, the product form will have a structure which is like umbrella caught by the wind. Okay, it is an inversion structure. Okay, so we will have this structure. Okay, maybe I can draw it clearly here like this. Okay, so now it's not the Br attached to the carbon anymore, it is the OH. Okay, so methanol is formed and the rate of this step is fast. Okay, because we are making new bond. Okay, so that's the product of this reaction. Okay, so Br will leave, okay, as the byproduct, which is Br minus anion. Okay, so in this story, okay, the C and Br has 3 small children. Okay, which are the H, H, and H. Okay, so it's easier for the backside attack to occur, easier for the carbon to cheat. Okay, so backside occur here, the OH is attacked by the carbon. Okay, OH is attacked by the carbon. Okay, and then the bond between C and Br is broken slowly. Okay, and then the transition state will be formed because because C has to decide which one that it wants, whether the OH or the Br. Okay, so Br is a good leaving group. Okay, easy to leave the group that attached to it. Okay, so Br make the decision to leave the family, and the new family is formed between C and OH. And when you want to make new family, when you want to make new bond, make sure you do it fast. Okay, so this is the mechanism, the answer for example 7.9 for mechanism Sn2 reaction.
Wow, this video has exceeded 1 hour. So as your homework, please do practice 7.2, question number 1. Write a reasonable structures of products formed when 1 iodobutane reacts with KCN, sodium hydroxide H2O, and excess NH3. Question 2, you need to identify what are A and B Both of them are positional isomers with molecular formula C4H9Cl. A is a primary haloalkane, B is a tertiary haloalkane. So you need to specify which will undergo Sn1, which will undergo Sn2 by drawing the structural formula of the products and writing the reaction mechanism for both of the types. Rate law. Let's look at how rate law comes into the equation. Now let's compare between Sn1 and Sn2. Sn1 involves two-step mechanism, but Sn2 has only one step. So Sn1 is called unimolecular rate determining step because the first step involves only one reactant. So it is a first order whereby rate equals to K concentration of Rx. Remember chapter 3, reaction kinetics. But because Sn2 has only one step reaction, it is a bimolecular rate determining step because we are going to use both Rx and nucleophile concentration as the rate determining step. So it is basically a second order following the rate law of rate equals to K Rx times concentration of nucleophile. Now, Sn1 will occur when we have weak nucleophile. Sn2 occur when we have strong nucleophile. Basically, OH minus and Cn minus are strong nucleophile, so they would usually do Sn2. Carbocation rearrangement would occur in Sn1, but in Sn2 there would be no rearrangement. And the reactivity order, the tertiary haloalkane, is reactive compared to secondary and compared to primary. Reactivity order for Sn2 is the methyl halide would be more reactive compared to primary haloalkane and secondary haloalkane. So thank you very much for listening to this very long lesson 70. I hope you would be able to understand the mechanism. Inshallah, it is going to be asked in the final exam, whether in your MCQ and SAQ questions in goal or in your individual assignment. Stay tuned. Assalamualaikum. Bye.